True. Now we're recording, having a discussion about the how to find this 4.7 estimate of the Pourbaix diagram of the endpoint in the alkalinity titration. So let's see if my pen works. And the alkalinity from previous was something like 2 times 10 to the minus 3 equivalent, or per liter, or 2 milli equivalent per liter. So this is then, if we interpret the alkalinity as the majority of the ions are HCO3 minus, and that is in this diagram depicted by the green line. You see it here in the label. It's a two protonic acid system. So the acid part is the carbonic acid. Well, if the concentration is 2 times 10 to the minus 3, then the PC should be something like 3, or maybe 2.7 in order to be exact. Maybe I have reused an old this 3 here could possibly be 2.7. But in the actual titration, we start, the titration curve looks something like this, and then the pH drops very much at the equivalence point, and this pH is as given in the exercise approximately 4.7, or at least not 5.6 at least, or sometimes one see 5.4, but considerably higher value in the literature. And why is that? It's a simple short answer is that this is because the alkalinity in natural water is so high, so that the total concentration, the P of the total concentration will be much higher than if it would only be due to dissolved carbon dioxide. But coming here, we consume the HCO3 minus. Here at the equivalence point, we have essentially only carbonic acid left. And so we have a solution with carbonic acid and water. And what can happen with that solution? It can lose some hydrogens and form HCO3 minus, and also water can lose some hydrogens and form hydroxide ions. Carbonic acid can't add any hydrogens, but water can add hydrogens. So then we should have an equality between the oxonium ions and the hydrogen carbonate ions plus the OH ions. Now let's see, where is this equality more or less indicated in the diagram? I suggest here, because then we have the equality between hydrogen carbonate and the black line, that is hydrogen oxonium ions. So these two, but what about the hydroxide ions? That is the purple line, and it's several units below, and on a logarithmic scale that means that we can skip this one. So that is the reason why that is the point. And what value has it? Well, if this is an equal-sided triangle, it's the average value between, say, 3 and 6.4, and in that case it become 4.7. If we instead would have draw it a little bit higher, then it if this intersection here would be 2.7, then the average value would be something like 4.55. Yes. And I think that's enough information to claim that this is probably the correct, more correct value than the can I can't move. No, let's see. The other diagram has a much lower total concentration. This is in the order of 10 to the minus 5. But that is the natural alkalinity that would occur if we would have dissolution of carbon dioxide from the atmosphere. The atmosphere contains slightly more than 400 ppm carbon dioxide. So that is together with the Henry constant in the dissolution of carbon dioxide to make up carbonic acid will give approximately 10 to the minus 5 here as a total concentration. And if we would be at such levels, then it would be more correct to have an endpoint at 5.7 here, so, which is more or less equal to 5.6 then, as recommended in the literature, somewhere in the literature. But they obviously, it's not a big difference, but do we have these do we have the old exam also? Answer at here, all three parts. Yeah, we don't have any titration curve. Do we have a titration curve for on the last year? I think so. Here is a titration curve, the red curve. This is a typical, and this is a real titration curve of natural water, and the well, sort of middle point on the where the transition takes place from hydrogen carbonate to carbonic acid is approximately here. And I would say that that is something like 4.5. 5.4 is up here. So it's not a big difference, but I mean, it's here that it starts to decrease. But I would say that a better equivalence pH for if you just want to have a look at equivalence point just by measuring pH and don't care to draw a curve, then it would be something like 4.5. It is, of course, much better to draw the curve than to rely on a certain pH value and choosing an indicator maybe. It won't do a very big difference, but a slight difference. Was that? Yeah.
Sorry, just to double check. So basically the point is that the equivalence point depends on the concentration or the alkalinity in the sample.
Yeah.
Okay, good, then I understood it.
Yeah.
And you said earlier, you showed that the equivalence point, to me, I've understood the equivalence point as the same amount of the two like moieties of
Yes.
sort.
Yeah.
Yeah. So they're this like the same concentration at the equivalence point, right?
Yeah.
Yeah. Okay.
If we draw one of these curves, now let's see pKa1 6 point. The pKa points, they are equal. But then say that we have a very high 0.1 moles per cubic decimeter equivalence point. Then we, do you see this logarithmic diagram?
Mm-hmm.
Then we would be at that point when we are ending up with a solution of H2CO3, which is less than 4. But then if we would redo this, now let's see, so and 6.4, 10.3, and maybe we set at 0.0001. This is the natural concentration of carbon dioxide. If it's only carbon dioxide from atmosphere that is dissolving in say deionized water, then we would get this concentration, and then it's close to 6 here, 5.7 or something like that. And suppose I can't draw, I can't simulate the titration curve with this software, but suppose you would have very, very pure water with faint, say that we have 10 to the minus 8 concentration of carbon dioxide, then we could interpret this as we're starting here on the hydrogen carbonate line. But wait a minute, what is this? It's lower concentration than hydroxide or oxonium ions. So this is pure water, approximately 7. It's not totally unaffected by the carbon dioxide, but I would say that the deviations from 7 in pure water, if it is 7, depending on temperature, of course, then it would be very, very small. So here there is no equivalence point, and in the previous 10 to the minus 5, there is a weak equivalence point, but it's hardly visible.
And it's on the middle species, HCO3 minus. What is that?
The middle.
What does that point mean, where you have the black line crossing the green line?
That doesn't mean anything.
Okay.
I don't think so. We can check. Suppose you have a very low concentration of hydrogen carbonate, then we could assume that would deprotonate and protonate, unfortunately, and the same applies to water and oxonium ions. So we should have the sum of those equal the sum of those, and that is actually that point, because the red line carbonic acid is well below a unit below, so we can neglect that. And here the carbonate, the blue one, it's well below the hydroxide ion, so we can neglect that. So this is pure water. If we have very, very low levels of acids and bases, in this case hydrogen carbonate, it doesn't matter anything. It doesn't affect the acid-base properties of the water. And that intersection, it doesn't mean anything. It's just an intersection.
Okay, that explains a lot. Thank you so much.
Yeah.
Yes, but so if we just summarize, when we go back to the question itself,
yeah,
you would know that 4.8, I think it would be a good endpoint, because when you look at the graph, you'll see that
it's somewhere there, and that you would expect equilibrium, or where everything is transformed to carbonic acid. Yes.
Okay, so essentially, in order to do this, you'd have to do this little where you put up all these pieces in the mixture and then see what they could react to, what could take up and lose protons, and then from that you'd have to then realize that it would mean that you'd have equivalence, or at the point where the pH and the H3O3 lines meet. So you'd also have to have the diagram.
Yeah.
Okay.
But I would, if I would ask this question now, I would give you the diagrams.
Okay. All right, nice. So I had another question about the exam as well. But that was about the exercise 2B, where you had a calculation where you wanted to calculate the ratio of nitrite to ammonium. And I just wanted to see if you could show the entire calculation, because it sort of skips steps in the answers. I just want to see if I did it the way you were supposed to or not. See, it has a little dot and then
Yeah. What did I do here? Yeah, you have this. The dot is. I don't think that is. That is just a printing error. It should be one dot. Punkt. You have this formula. So when you have the reaction, so I should show the reaction. There it is, and then annotate. When you have that one, and you know that PE is 10 and pH is 7. So what was the question? The actual fraction of ammonium and nitrates?
Yes,
Yeah.
and you also had the info that the PE0 was 15.
15, yes. So then this is 10. Yeah, you have it here. And number of electrons are 8. And then Q is the right hand divided by left hand. Here the water is, this is a dilute solution, so the water is replaced by a unit. Otherwise it's perfectly okay. So and pH was 7, so this is 10 to the minus 7 raised to the power of 10. And what I did, how did I do it? Yeah, I would say that 10 minus 15 times, that is minus 5 times minus 8 in order to get that is the logarithm. What is this? 10 minus 15 is minus 5 times minus 8. Minus 5 times minus 8 is 40. So that is the logarithm of NH4 plus divided by NO3 and 1 upon 10 to the minus 70. So then this is the logarithm. So then removing the logarithm is taking 10 to the 40 equals this thing. And then we multiply by 10 to the minus 7. And we should, is there something strange here? 40, 70.
Is it really minus 8? It's 1/8, isn't it?
Yeah, but when you move it to the other side.
Yeah,
Oh.
if we multiply by 8, then or minus 8, then we
Right.
Yeah, because maybe it's the same thing, because I tried to use like the logarithm laws to break out the minus 70, and I got, it was really similar, but I got 30 instead of 20.
Yeah. That is perhaps correct. 70 and 40, and then the difference is 30. Yes, that's true. So
okay, so because what I did was it was a division there within the logarithm.
Yeah.
So I put it on the outside, you know, like
Yeah.
a subtraction.
Yeah.
And then you could calculate all of that, and then you had the logarithm of 10 to the minus 70. You know, it became just, you know, like 70, and you remove it on the other side. You get minus 30 instead.
Yeah.
So that's what I think that, because it seemed correct in my head, but it wasn't the exact same. But maybe
but there is unfortunately, I think you're correct. This is 10 orders of magnitude erroneous, but
okay. I mean, but that's good. Then I know that I didn't lose some numbers or something.
No.
Thank you.
Yeah. I can change this solution and upload some extra line here.
We can email you, right, Rosh, if we have any issues with the exam. Yeah, great. Because I haven't really sat with your part yet.
No.
All that much. So I don't have any questions right now.
Yeah, I had the question. It was the same question I got into earlier with the alkalinity.
Yeah.
I got a little. It's not entirely clear, or it hasn't been entirely clear, like what the concept is for and what's good with it. It's because from what I like, understand right now is, it's like they say that when I read about it, they say on Wikipedia, they said it's like the opposite of the acidity or something like that.
What is what?
The opposite of acidity or something like that.
Equivalence. Or alkalinity.
Maybe it wasn't on the. They said that it was the opposite of acidity or opposite of something. I don't know where I read that, but could you think about it like you have the pH, but then you have the pOH, and it's the alkalinity like the pOH, but including all other anions.
Yeah, it's approximately the concentration of the basic ions, and it's more or less only the anions that is contributing to making the solution accepting hydrogen ions. Otherwise, the acidity, as you said, that is the concentration of acid. And very often acid ions are cations, but I mean, hydrogen carbonate is, so perhaps we should skip this N and cat. As acid ions and basic ions make up acidity or alkalinity or basicity, we could call it also. Acid neutralizing ANC, actually, acid neutralizing capacity.
Okay, and then the other thing about I got some time to think about the equivalence. Like I understand the fact that like a basic anion,
yeah,
with 2 charge could neutralize 2 hydrogen ions or
exactly.
So I understand that.
And that is the only thing. I mean, say that you have 1 molar solutions of each of these 2. So exactly what you said, that 1 mole of the hydrogen carbonate will consume 1 mole of hydrogen ions only, but 1 mole of carbonate will consume 2 moles. So then you can say that if you want to give the concentration in moles per cubic decimeter, then it's kind of okay, both of them. But on the other hand, if you give the concentration as the equivalence per cubic decimeter, you assume that how many places for hydrogens or how much charge is it. So then this one would be 2 and this one would be 1 then.
Okay, but like still like so if I had this unit, the equivalence per liter or cubic decimeter, it's like, okay, 2. So if I have 2, or if I would multiply this by 2, then I would multiply, I would take 1 liter of whatever has 2 equivalent per liter. If I take 1 liter, what does that mean? Does that mean that I can neutralize 2 moles of acid?
Yes.
In that liter.
Mm.
So that's it. That's then I think that's
the only thing. There is nothing more to there is nothing more hidden or anything like that. Nothing strange about this. I'm not sure. In a way, you don't need this concentration measure. It's quite enough with moles per cubic decimeter. This is the concentration measure that we have been that we are using in almost every other respecting chemistry. Maybe we can also say moles per kilogram of solvent or something like that. But in at least in our courses, it's not so common. But with water, they will be equal.
Okay, so it's basically like it's useful because it makes it clear.
Yeah.
Like you don't have to understand what the charge is and what that means for the neutralization. If you have the equivalence, it doesn't matter what charge it has, or if you know that, maybe.
Yeah. But
is there an ions that has a particular charge, but don't have that same charge as an equivalent, like the value, like for example, something that could neutralize 1.5 hydrogens, like it just theoretically or something.
No, I don't think so. Say that you have the 3 common ions in ocean water. Say that this is 1 moles per cubic decimeter. And then we have the common ions and the anions, and the sulfate and the chloride. These are the major ions, and they are, now let's see, 0.8 moles per cubic decimeter.
Okay, that's outside of the whiteboard now.
Let's see if we can. Do you see it now?
Yeah.
So this is very strange. I haven't because why isn't the concentrations equal? But if you do it in equivalents, maybe this would be something like 2 equivalents per cubic decimeter, and then I realize now that don't take these values for granted, but in equivalence they should be exactly equal. Otherwise, the amount of the sum of all plus must be equal to the sum of all minus charges. Otherwise, the water is charged.
Yeah. But how now it's not the same charge anymore. So the equivalent doesn't need to be with protons, like.
No. It's just charged particles. Then with non-charged particles, then the equivalent concept is hardly useful.
Okay, so it's basically just the
taking the charge into account.
Yeah, how the balance would be in the reaction, basically.
I can draw this on paper a little bit more careful and with correct values for seawater, and then you will see that the concentrations, they don't equal each other, but the concentrations expressed in moles per cubic decimeter. Because there are some ions that are 2+ and some that are 1+, and but it's not the same amount of different ions with charges on the negative side. In seawater, this would be totally dominating, on the other hand. So these two are much more than any one of the other ions, but we can make a lake water. So these two should be equal to these two if you count in equivalence. Otherwise, it's something fishy. There can't be more positive ions than negative ions, or vice versa. And then it's something that we don't know. For example, fluoride ions or. But I think we could actually check with your calculations. Where are they?
I think I understand. Anyways, that's an answer to my question.
Yeah.
Like yeah, but it's just basically the concentration kind of the basic or the anions, as well as you take into account the balance in the reaction.
Yeah.
All right, thank you.
So here we had the alkalinity is not very high in Lake 1 here, but there is a lot of calcium magnesium ions, but that must be compensated by the sulfate and chlorine. I haven't made any calculations to see how well these two fit each other, but in principle the alkalinity plus the sulfate plus the chloride, they should equal the calcium and magnesium. And yeah, then we don't measure sodium because that is difficult to measure. So perhaps chloride and sodium are equal. So then it should be alkalinity and sulfate that are equal to calcium magnesium essentially. And that should fit for most lakes.
I didn't really get that, what you meant there.
Yeah, if we, and the alkalinity, if that is hydrogen carbonate and sulfate ions are present in water, and they are the negative ions, and calcium and magnesium are the positive ions, except sodium and chloride. So then the amount of negative ions should be equal to the amount of positive ions. Isn't that reasonable?
Yeah.
At least when it comes to, I mean, some ions are 2+ and some ions are 2-, and some are 1-. So you need to take this charge into account.
Or would that be the equivalence?
Yeah, then it's very convenient to have the equivalence measure.
But why didn't you count chloride as well?
Yeah, because we would need to have the sodium also, and I think here at the two freshwater lakes, then you can count the chloride ions also, 5 millimolars. Yeah, they're quite high. So we don't have the sodium, so that is missing information.
Oh, I see. So it's you can't do the chloride because it would mess with the balance, because we didn't count the sodium.
Yeah. I think that at least in the salt lakes, Lake 1 and 4, the chloride is approximately only coming from dissolved sodium chloride. So, but that is not for sure. I mean, it could come from vitrification of some clay minerals also. But well, approximately the alkalinity and sulfate should be equal to calcium magnesium. 2.64 millimoles. That is 2.64 plus 14, then 2.6 and 1.4, that is 3, 4. Is 4 equal to 6? Yeah, maybe not. But I mean, it could be something that we are missing. Aha, battery low. I need to find a source for my computer soon. Any more questions? I stop this chart. Stop. Nu ska vi se här. Stop this. Nej, inte så. I stop this record.